Okay, hello everyone. I'm Alessandro di Federico, and as I've been presented, I'm currently a PhD student in Politecnico di Milano, but I've been doing this work while I was working at UCSB with some other fine guys like Amat and Jan and my two advisors, Giovanni and Christopher. Okay, so let's see what are we going to see today. Today I'm going to try to present to you a technique which basically allows you to call arbitrary library functions without the need for a memory leak and bypassing specific protections like ASLR and RELRO. And probably most of you don't know what RELRO is, but we'll see it. So let's try to review the usual exploitation process. So first of all, you want to find a vulnerability, and you want this vulnerability to be useful. And by useful, I mean that it's able to get you the control of the IP, of the instruction pointer. After you get the control of the IP, then you can perform the desired actions, such as calling the system library function, execv, reading a file, all these kind of things. Our focus in this presentation is on the last step. So how can we call arbitrary library function under certain conditions and in presence of certain protections? Because just getting the IP, it's not enough. Once you have the IP, you want to understand and find an interesting location where you can point this IP, the instruction pointer, to perform the actions you want. And typically, if you have like a non-PIE binary, so the main binary it's not relocatable, it's in a fixed position, what you do to bypass ASLR, which is your enemy, because it basically scrambles the position in library at runtime, what you do usually is you exploit a memory leak vulnerability to get the address of unimported functions, for instance, printf. And then if you have a local copy of this target library, you compute the distance between printf and another interesting function, for instance, execv or system. And with this information, you can compute the actual position on your target of the target function. So in this case, execv. This works, but it has some problems. So first of all, you need a memory leak vulnerability, which is a distinct vulnerability from the one that's giving you control of the IP. And you might not have it. It's not always present, or it might be hard to find. And also, it requires knowledge of the layout of the library. You need to know the exact distance between printf and xv. And if you don't have a copy of the library, you cannot do this. So for instance, if your target is using, I don't know, Gentoo, they're building all the libraries by themselves, this attack is not going to work. And finally, a thing that usually people don't think about, you also need a communication channel back to the attacker. So if your exploit is deployed to, for instance, an air-gapped machine, you will not have a communication channel back to the attacker, and you will not be able to leak the address of printf and perform the so-called two-stage attack. So we're going to try to face these issues. But let's try to rethink the attack. What are we actually trying to do? What we want to do is get the address of an arbitrary function, obtain its address. But if you think, well, we already have an operating system component which does that, and that's just the dynamic loader. So let's try to look into the dynamic loader a bit. So the role of the dynamic loader is taking a binary, an ELF binary, go through all the imported functions and get their address from the dynamic library that have been loaded in memory. But nowadays, this process is not done at the beginning. You don't run through all of the imported functions at the program startup, but you do that in a lazy way. In fact, ELF supports the so-called lazy loading, which means that a certain function is you get the address of a certain function only the first time you call it. So if you never call it, you're not going to waste time looking for it. So let's see how the lazy loading works. So this is what you are usually used to think about as a simple hello world program. But what actually the compiler emits, it's not a call to printf, because it doesn't know where printf is going to be at runtime due to ASLR. What it's actually going to emit is something like this. It's going to emit a call to a trampoline, which we call here, which is called printf at plt, which more or less looks like this. So this is implementation of lazy loading. So the first time you call this trampoline, the control will go to the dynamic loader, in particular to this DL runtime resolve function, which we'll see multiple times in this presentation, whose first parameter is a pointer to a data structure which is internal to the dynamic loader and contains some useful information about the current ELF object used by the dynamic loader, and a second parameter which is an identifier of the function you're trying to resolve. This DL runtime resolve function will find the printf function, looking for it in all the loaded dynamic libraries, and it will store its address. It will basically cache its address in the GOT, in the global offset table, and then it will also call it. This is important. It's not just going to find and save the location somewhere. It's also going to call it. And from the second time on, you call printf at PLT, you will not go through all the dynamic resolution process, but you'll just call the function, the cached address, which is stored in the GOT entry corresponding to printf. Okay. So this is what looks like the data structure which DLL runtime is gonna deal with. So DL runtime has this identifier printf index, which is actually an index into the relocation table. A relocation table is a table composed of relocation, which are basically directives for the dynamic loader. And what we're interested in this directive is that they keep a reference to a symbol, and they keep this reference as an index in another table, which is their symbol table. And in turn, the symbol table is composed by data structure which keep a reference to the name of the symbol they represent. So you can imagine a symbol as something representing either a function or a global variable in a dynamic library. In this case, we're just interested about functions. So basically, the relocations in relocation table keep a reference to the symbols in symbol table as an index, and the symbols in symbol table keep a reference to the name in what is called the string table as an offset starting from the beginning of the table. So for instance, if we call DL runtime resolve with printf index, it will first go to the relocation corresponding to printf, then it will go to the symbol corresponding to printf, and then it will get to the string corresponding to printf. So all of this data structure are in read-only memory areas because they are not supposed to be modified at runtime. They're just static information. This information will be useful afterwards. So let's try to see what kind of attacks we can come up with in this setting. Some requirements. So suppose we are able to start a ROP chain, and we are able to call this DL runtime resolve function. And this is a reasonable assumption because the address of DL runtime resolve, it's always available in a reserved entry of the GOT. So we have the address of this function, which is basically our interface with the dynamic loader. And also, we assume to have at our disposition some simple gadgets which allow us to write arbitrary memory area, and they have to be in the main binary. Remember that we are assuming that the main binary is not PIE, so we know the position of the gadgets, right? So if we are able, if you have this, if these assumptions hold, what we can do is we can try to trick the dynamic loader into using a fake string table. So instead of, if you're able to trick the loader into thinking that the string table, instead of it being the real string table, it's some memory area that it's under control, we can build a fake string table there with, for instance, where we replace at the offset where printf should be the string of execv. I'll explain this. So in the .dynamic section, where there are some useful information for the dynamic loader, there's also an interesting thing. There's a pointer to the base address of the string table, which I remember you is the table keeping all the list of the symbol names. So if we are, this .dynamic section, it's actually writable, okay? So if we write there, if we overwrite this pointer to the base address of the string table, we can trick the dynamic loader into thinking that actually the string table is in a memory area we can write to. For instance, I chose BSS, which is just a writable section where usually uninitialized global variables are. And if we write it in BSS, something that looks like a string table, but at the offset where printf should be, we have execv. If we call the L runtime resolve with the index of the relocation corresponding to printf, the dynamic loader will go through the process that we described before, but it will end up finding the execv string and not the printf string. This means that it will resolve and also invoke the execv function. And so basically, this is the basic concept which allows us to call an arbitrary library function. This is all very nice and works, but it's something that is well known. In fact, the developers of linkers have developed a protection, a binary hardening protection known as RELRO, which stands for RELocation ReadOnly, which aims to prevent exactly this kind of attacks. RELRO comes in two flavors, partial and full. So let's first see the partial RELRO flavor. So why the .dynamic section, the one where we were tampering with, is writable? basically because some values in there have to be initialized at runtime. What partial RELRO does, it simply says, okay, after you initialize the section, just mark it as read-only. So if someone tries to tamper with it, it will get a segfault. And this, as a result, prevents the attack that we just described. So we explored a bit more, and we tried to come up with another idea. Let's look again at DL runtime resolve. The printf index parameter, the identifier of the relocation, what happens if we put a value that is a very large value, a value that is larger than the number of available relocation? Well, it turns out that the dynamic loader will start going through the sections coming after the relocation table. So the relocation table is stored in RELPLT. So let's see what's after RELPLT. This is simply a list of the section of a random binary. So after RELPLT, if we put an index large enough, we'll go through dynamic, GOT, and then we'll end up in BSS. So the idea is to invoke the L runtime resolve with an index that is large enough to trick the loader into looking for a relocation in a memory area which is writable, which is under our control. And so, for instance, here in BSS, we'll forge there a fake relocation data structure which will allow us to resolve an arbitrary library function. So let's see how this works. So typically, we said that printf index will point to some entry into the relocation table. But if we put an index large enough, we can trick the dynamic loader into looking for a relocation in BSS. And then the relocation, as we said, also needs to keep a reference to a symbol. And we use the same trick again. So we put a symbol index, which have to be big enough to go over the end of the symbol table and get to BSS. For the symbol name, same story. So we put an offset inside the string table, which is large enough to end up in BSS again. And so basically, and then we can just write the string of the library function we're interested in calling. So basically, we're just forging all the data structure which are needed by the dynamic loader to resolve a function in the BSS section or any other writable section. And calling the DL runtime function with appropriate index, we can trigger the resolution and execution of this function. In this way, we're basically able to bypass the partial RELRO protection because we are not writing in the .dynamic section. Okay. So also this approach works, but not always. In particular, there are two cases. The most obvious case is, okay, what if the dynamic loader checks the boundaries? For instance, what if the dynamic loader checks, okay, but you gave me a printf index which is too large? Actually, this doesn't happen a lot, but we'll discuss this. And the other situation where this approach does not work if you have a 64-bit binary with symbol versioning enabled and huge pages enabled. I'm not going to discuss why this is a problem. You can find more details on this on the paper. But let's just say that this technique is effective, but not in all situations. So we came up with another idea. So far, we explored the meaning of printf index. But let's look into elf-info. So elf-info is a pointer to a data structure of type link map. And the nice thing is that we always have a pointer to this data structure, which is an internal data structure of the dynamic loader describing the current elf object. We have a pointer to this data structure in the GOT. There is a reserved entry for this data structure, for a pointer to this data structure, just as the runtime resolve. But even better, this link map data structure holds a pointer to the base address of the dynamic string table. So the idea is, if we are able to tamper with this data structure and we are able to change the value of the base address of the string table, basically we can go back to the first attack I presented, okay? Let's see how it works. So in the GOT, in the second position, we have a pointer to this link map data structure. In this link map data structure, now we don't really care about the exact layout, but let's just say that there is a pointer, this pointer, which is used internally by the dynamic loader as the base address of the string table. So usually it points to the real string table, but if we are able to write there, we can make it point to BSS and basically just go back to the first attack I presented. And so again, we're able to bypass partial RELRO even in the presence of even if there are boundary checks and all the other situation I described before. Okay, let's now look into the other kind of protection offered by RELRO, which is called full RELRO. Basically, full RELRO just completely disables lazy loading. And This means that some pointers in the GOT are not initialized. In particular, the pointer to DL runtime resolve, which is, I recall, our interface with the dynamic loader, and the pointer to the link map structure, which we just abused, are not initialized. Simply because disabling lazy loading, everything is initialized at the program startup, and so basically it's not needed. They don't have to be there. It will be just useless. But for us, it's a problem because then we cannot perform our attack, right? But it turns out that we can abuse a debugging feature to get the address of link map. Let's see how. So the .dynamic section, which I recall, it's a section that just keeps some useful information for the dynamic loader, has an entry which is called dtdebug, which keeps a pointer to a data structure which is used by debuggers, for instance, by GDB, to be able to break on certain events, such as the loading of a new library and other stuff, which we're not really interested in this. But the nice thing is that this data structure also holds a pointer to link map. So basically, even if the GOT is not initialized with a pointer to link map, through this debugging data structure, we're able to get to link map again. Nice. But we're still missing something, because we said that also DL runtime, the pointer to DL runtime resolve, it's lost with full RELRO. But the idea here is so usually full RELRO, at least in Linux distributions, is applied only on critical binaries, like binaries that are very important, such as SSHD or, I don't know, Apache and these kind of things. But it's not applied to dynamic libraries, because if you applied full RELRO to dynamic libraries, you're not just going to affect the critical binaries, but you're going to affect all the application using that library. For instance, if you apply full RELRO on the C standard library, you're basically going to affect, and also from a performance point of view, because full RELRO has a performance cost, all the applications. So the idea is that even if the main binary is full RELRO, and in its GOT we don't have a pointer to the L runtime resolve, in the GOT of all the dynamic libraries, we still have that pointer. So if we have a way to reach the GOT of a dynamic library, we're going to be able to get the address of the L runtime resolve. How can we do this? Well, it turns out that the link map structure, with the data structure which we were corrupting before, as the name suggests, it's part of a linked list. A linked list of the same type of data structure, which basically describe all the loaded ELF objects. So the one that we first have is just describing the main binary. But if we dereference then the pointer to the next entry in the linked list, we'll get to the data structure describing the first loaded dynamic library. And from that data structure, we can find a pointer to the GOT. And basically, from its GOT, we can get, again, to the address of DL runtime resolve. I'll try to explain this again. So we start from the .dynamic section of the main binary, and from its dtdebug entry, we get to this debugging data structure. We don't really care about its layout, but the important thing is that it has a pointer to the link map data structure. So as usual, as we did in the previous attack, we are tampering with this pointer, and we are changing the base address of the string table. But this is not enough, because then we dereference the lnext pointer, which is just a pointer to the next element in the linked list, and we get into the link map the data structure describing the first loaded dynamic library. And from there is a pointer to the GOT, and from the GOT we go to the third entry, and we have a pointer to the L runtime resolve. So we basically have been able to change the base address of the string table, and we have been able to recover the address of DL runtime resolve. We can perform our attack again and also bypass a full RELRO. Okay, so let's see how we implemented this. Basically, we implemented leakless, which implements all of the techniques I've been presenting, and if given a binary, it automatically detects which one of the techniques I presented is the most suitable one, and it can produce two different kinds of output. It can either output some high-level instruction on how to perform the attack, like use this printf index when you're calling the L runtime resolve, or write these bytes representing some data structure at that address, like outputting them in a JSON and some high-level, so just high-level instructions. Or, if provided with the appropriate gadgets, it can also produce directly the ROP chain implementing the whole attack, which is kind of nice. You can find the source code of leakless at that address, github.com/ucsb-seclab/leakless, and I invite you to check it out. So we've been talking about gadgets. What kind of gadgets we need, and how many? we need up to 4 gadgets depending on the kind of attack we need to use. So all of the attacks need the simplest gadget, the memory write gadget. So you give to this gadget a destination address, a value to write there, and basically the gadget should write that value there. From the third attack on, we need to tamper with some data structure. And so we need basically this kind of gadget. You give it a pointer to the data structure, you give it an offset in the data structure, and a value to write in that data structure, and this gadget is supposed to write there. The last attack, the one bypassing also full RELRO, needs 2 additional gadgets I'm not going to present. You can find more details on this on the paper. But the key idea is that I've been annoying you with 4 different techniques because they have different requirements. So if you're able to apply the first technique, it's easier. You just need a single gadget. It's easier to find, it's easier to implement. Otherwise, depending on the protection, you need more sophisticated attacks. Okay, now let's try to evaluate the impact of this technique. In particular, what loaders are vulnerable to this attack? So we tested leakless against the glibc dynamic loader, which is the most popular dynamic loader under Linux distributions, and against the FreeBSD dynamic loader. We deem the glibc dynamic loader it's vulnerable, but by manual inspection of the source code, we also consider that dietlibc, uclibc, and ulib, which are popular C standard libraries for embedded system, are vulnerable, and also OpenBSD and NetBSD dynamic loaders are vulnerable. So the Bionic C standard library, which is used in Android, it's not vulnerable because it just supports PIE binaries. And Musl, it's an interesting case because it's kind of safe because it simply does not implement the functionality we rely on to perform the exploitation, which is lazy loading, which is, in this case, the missing of a feature. It's kind of a feature itself, if you want. For FreeBSD, we have a particular discussion to do because it was the only dynamic loader actually checking the boundaries of the input. So when you pass to the L runtime resolve an index, it's going to check if it's too big or not. So it's not vulnerable to the second attack I presented, but it's still vulnerable to all the others. Let's try to recap and see what countermeasures we can come up with to prevent this kind of attack. So as we said, the leakless provides you with a way to perform an exploitation in a single stage. So you don't need a memory leak vulnerability, you don't need interaction with the victim, and so you don't need a communication channel back, even if offline attacks are feasible. It's also reliable and portable because if leakless works, if it's able to build an exploit, it's going to be deterministic. There's no guessing involved. And also, you don't need a copy of the dynamic library you're targeting, which is something pretty interesting. And also, since it basically relies on standard ELF feature, it's very portable across all the ELF-based platforms. And so it was quite an impact. The only exception to this is the layout of the link map, that data structure, which depends on the specific dynamic loader, but they are seriously minor changes. It's really easy. Also, if you want to get the same level of reliability and you want to be able to perform the exploit on a single stage, the equivalent technique before leakless will be just re-implementing ROP the behavior of the dynamic loader. And if you have a Turing-complete gadget set, you can probably do that, but building a Turing-complete gadget set, it's not easy, and in any case, it's going to produce way longer ROP chains. And as you know, buffers are usually limited, and so having a shorter ROP chain and reusing existing program functionality, it means that the attack is feasible in more cases. You can find some evaluation on this on the paper. Finally, we also think that leakless can produce more stealthy attack, because one might say, okay, why not just use syscalls, right? Syscalls. If a syscall is available, which is not always the case, we think that it's a more invasive approach under certain situation, because you might have seccomp, you might have app armor, or you might have intrusion detection system monitoring the syscall you are performing. Instead, if you reuse the existing program functionality, you can be more stealthy. For instance, we have this example in our paper of Pidgin. So Pidgin is just an instant messaging client. So suppose you want to intercept the traffic of a user of Pidgin. You can do that with syscalls most probably, right? You can do basically everything. But if you reuse library function, it's way easier. For instance, here we're getting with the first function, we are getting the global, the object describing the global proxy setup. We're just setting an host name. we're setting a port, we're setting a proxy type, then we reuse library functions of Pidgin to get the account of a user, and we disconnect it and reconnect it. And from now on, it's gonna use our proxy. So you can do this with syscall, but it's gonna be way harder and it's gonna be more intrusive. And finally, last but not least, it's also automated. So if you're able to provide the gadget set that leakless needs from 1 to 4, you can basically have the ROP chain automatically generated. The countermeasure, so basically the obvious countermeasure is to use PIE, but even in the presence of PIE, we think that if you have a memory leak vulnerability, you're gonna be able to, leakless is still the most efficient way to be able to call an arbitrary library function. Or you can use full RELRO everywhere, so not just on the main binary, but still this will obviously incur in some performance overhead that you might not be willing to pay. Another interesting countermeasures might be disable DT debug if not necessary. For instance, the dynamic loader could initialize that field only if they're in presence of a certain debugging, in presence of a certain environment variable that indicates that you're in a debugging context, right? Because usually the user do not need that feature. And another option is to make the loader's data less accessible. So instead of putting a pointer, for instance, to the link map data structure, you might put an index that the loader will then use to index an array of pointers in its private memory. Or finally, the most radical solution is completely isolate the dynamic loader from the application. For instance, if you're using a microkernel, for instance, I'm thinking about Symbian OS, the dynamic loader is completely in another process. So there's no way in which you can tamper with its data. So in conclusion, we think that binary formats and these core system components, such as the dynamic loader, should be designed and implemented with security in mind. Because when we were surveying all the dynamic loaders, it was clear that, for instance, the implementation of the L runtime resolve were trusting the user input because they just assume, hey, the compiler is going to emit this code for me, what bad could happen? But this might not be the case, and if it happens, we have these really reliable and portable exploits, and it has a quite wide impact. And with this, my talk is finished, and thank you, and I'd be happy to take questions.
Okay. Have you considered different type of platform like Windows PE format so that you can argue that this is the fundamental problem of the dynamic loader or specific bugs in the implementation?
So we tried to consider Windows, but the key thing is that nowadays under Windows, PIE is applied everywhere. So it's less of a problem. But you might have a similar possibility, but we deemed that it was less interesting. For Mac OS X, it's the same reason. So yes, we briefly look into that, but it was less stimulating for us, let's say.
Also, if you're targeting the PIE disable binary, so at the first place, this is very vulnerable. There you can apply tons of different techniques to exploit that. Do we have to use your technique to exploit this particular binary? So what if we could just copy the address of system library call and just use it as it is?
So you can perform a call to system if the system function is imported. But if it's not the case, you have to find a way to get the others. And if you don't want to use a memory leak vulnerability because of the reason I explained, you can do that. So yes, I mean, it's true, but in several cases, this is a very useful technique. And also, I want this to be a paper like stimulating distribution to start using PIE all over the place, because there's really no reason nowadays why it should not be used.
In my understanding, sorry, Patrick Hewlin, MIT Lincoln Lab, in my understanding, binaries with PIE typically have a lot of sort of IP relative reads and writes. So doesn't that mean can you maybe find gadgets that have IP relative reads and writes to do something like this too, or is that not really possible?
I'm not sure I'm understanding.
in my understanding, and correct me if I'm wrong, PIE binaries often have these writes and memory reads and writes that'll be relative to the program counter.
So you're talking about PIE binaries?
Yeah, in PIE
Okay, but
binaries.
with PIE binaries, the problem is that you cannot even start the attack because you don't know where a single gadget is. You don't know where all
right,
the
you
data
can't-
structure
yeah, okay,
are.
Okay, thanks.
So you need at least a memory lake.
Okay, if you don't have more question, let's thank our speaker again.